Now that we have a better understanding of our decibels, let's look at our Bode plots. So one other thing to note though, before we get into our Bode plots in earnest, is that our Bode plots are going to give us a good first order approximation, but they're not going to be as good as doing a computer simulation. And so by as good, I mean it's not going to be as accurate. So not as accurate as simulation, and so we're going to point out a little later on exactly where sort of the main discrepancies are between this approximation and the simulation, but for now just know that this is going to be a pretty good approximation. And so what is our Bode plot actually consist of? Well, it actually consists of two semilog plots, and so what these two semilog plots are is the first one is going to be the magnitude of our gain. So this is sort of our magnitude information of our transfer function. So this is in dB, and it's plotted against our frequency. And the second plot of our two semilog plots contains our phase information. So it's going to have our phase in degrees, which is also plotted against our frequency. So before we go further talking about our Bode plots for our transfer function, I want to address sort of what exactly we're talking about when we say semilog. So our semilog plots means that we have one axis is a linear scale and the other axis is on a log scale. And so on the next page here we can see an example of some semilog graph paper. And so in this case, we see this side over here on the left is our linear side. And so we can tell this is linear because the sort of markings between spaces are even. So for example, if we say this is 0, 5, 10, we're just going up in even increments. So these sort of smaller sort of increments here would be 1, 2, 3, 4. So we have even spacing between them. So now down here on the bottom though, we have our log scale. And so we notice that as we go through these sort of large black bars, we are jumping by an order of magnitude. So we're going from 0.01 to 0.1, 0.1 to 1, 1 to 10, 10 to 100. So we're multiplying by 10 for each jump. So from here to here is times 10. The other thing you'll notice is that the lines in between these two major grid lines, or these major grid lines, more than two, are not evenly spaced. And so the way we would read that is, for instance, if we look at 1 and 10, because I think that's the easiest to sort of to grasp, is this line is 2, here's 3, 4, 5, 6, 7, 8, and 9. So we notice they get more bunched up towards the end there. So that's just sort of a quick overview if you've not ever worked with log plots or semilog plots before. Okay, so now let's go back to this idea of how do we represent this transfer function using our Bode plot. So we want to be able to plot our magnitude and our phase information. Well, in general, remember, we said that our transfer function is some magnitude of h, and some phase, phi. And so if you remember back when you defined phasors for the first time, so we said this is magnitude of h, and it's actually magnitude of h times exponential of j phi. So that was our definition of a phasor. So if we think about this more general definition, what we can say is, well, let's take the natural log of that. So natural log of h. From log properties, we have the two things multiplied. So it's going to be log of AB equals log of A plus log of B. So we have log of the magnitude of h. Flipped my bracket and bar there. Log of magnitude of h plus the log of e to the j phi. And so of course natural log and e are opposite functions, so we'll still have this magnitude, log of the magnitude of the transfer function. And now we'll just have plus j phi. So this is kind of where we see that we are taking the magnitude of our gain in dB, So that dB is where we get that sort of log. We're not doing natural log, but similar property, similar idea. So basically for our magnitude plot, what we're going to have is we're going to have the magnitude of h in dB is equal to 20 times log base 10, and let me clean that up, that was kind of messy. 20 times log base 10 of the magnitude of h. And then for our phase information, we see it doesn't have a log, so that's why we're just plotting the phase in degrees versus frequency, and we're not putting that in decibels. So another thing is that because of our log properties, so we're going to be able to add different segments of the Bode plot. So let's just say our log properties. So this will make more sense once I write up our other general equation here. So log properties, particularly this log of AB is equal to log of A plus log of B. And so what that means is basically if we have components in our transfer function A, B that are multiplied together, we can then add different segments to make our Bode plot. So we can look at log of A separately from log of B, and then we add them together. So add different segments of Bode plot to get sort of our overall Bode plot. So in order to get a better view of how that comes into play, let's consider another generalized form of our transfer function. And so remember back in our first video, I said we can have a couple different generalized forms depending on what we're looking at. The first one we looked at was looking at poles and zeros. And here we're going to look at something called our standard form. And so again, it's the same information just kind of presented in a slightly different way, which is going to be more useful for what we want to show here. So for our standard form, we have our transfer function in terms of j omega is equal to, and we're going to have a big old fraction here. We have some constant k, which is just along for the ride. We have j omega, which can be to the plus or minus 1. In the numerator, we also have 1 plus j omega divided by z1. So z1 is going to be a 0. So we see we still have these zeros, and we're going to see later poles still hanging out, just slightly different form. And then we have this more complicated term in brackets, which is going to be 1 plus j2 zeta 1 omega divided by omega sub k plus the quantity of j omega divided by omega sub k squared, and so on. And then in the denominator, we have 1 plus j omega divided by p1. And we have another big term similar to what we saw in the numerator, 1 plus j2 zeta 2 omega divided by omega sub n plus the quantity of j omega divided by omega sub n squared, ... And so basically these are all the different forms that we could sort of reduce our transfer function to. So if we sort of factored things out, we could see we have ultimately 7 possible terms. And so let's sort of look at each of those here. So we of course have our constant here. We have our j omega, which could be plus or minus 1. So we get 2 from that, so that's 3, 4, 5, 6, and 7. So basically we're saying no matter what type of transfer function we have, we can always somehow relate it to these 7 possibilities. So what we're going to do is we're going to, in future videos, look at each of these possibilities and say, what does their magnitude plot look like? What does their phase plot look like? And then we can plot each one in turn. And remember what we said here, using these log properties, if we have A times B, which we see, for instance, if we if we come down here and we say we have a j omega times this 1 plus j omega over z1, that's like our A and our B, right? So we have A, B. So we could plot the response from A, plot the response from B, add those two segments together to get our overall Bode plot. And so that's kind of the idea that we're going for here.